Everyone, and thanks for joining us today. My name is Matt Willard, and I'm the Senior Marketing Manager at Fluence Analytics. Before we get started, I want to point out the chat feature at the bottom of your screens. You can use the chat feature to make comments during the webinar or to pose questions to our panelists, which he will answer at the end of the webinar. Fluence Analytics is a startup headquartered in New Orleans, Louisiana, that spun out of Tulane University in 2013. We manufacture industrial and laboratory monitoring systems that produce continuous data streams and enable real-time optimization. This leads to improved process control and faster R&D. Today's webinar will discuss the fundamental origins of light scattering and how the technique's use as a characterization tool has evolved with the growing needs of the biopharmaceutical industry. Our panelist is Professor Wayne Reed, co-founder and CSO of Fluence Analytics and the inventor of all technologies contributing to the company's product portfolio. He is the Murchison Mallory Chair in Physics and founding director of PolyRMC at Tulane University. He has authored over 150 publications and is listed as an inventor on more than 30 issued patents and applications. Again, thanks for joining us today. Now I'll turn the webinar over to Professor Reed.
Okay, thank you, Matt. So as Matt said, we'll do just an overview of light scattering, not go into too much depth on any one thing. Starting at the beginning, we're dealing with light as an electromagnetic wave. Quick view on that is it's a transverse wave where you have an electric field in one direction and at right angles is the magnetic field, and the propagation is perpendicular to both of those directions. We live here in the visible light spectrum, roughly 400 to 800 nanometers. And as we know, as we get shorter, we're into the ultraviolet regime. As we get longer, we go into infrared and microwaves and radio waves. And you can see the scales of the different objects that would be comparable to light wavelengths here. The actual scattering has been observed, obviously, since prehistoric times, an atmospheric phenomenon in the oceans and lakes. But it was Tyndall in the 19th century who really put his finger on it being due to light passing through dispersions of very small particles. And in this photo here, you can see a laser beam going through a cell just with water, and you see virtually no scattering at all. But when you put little particles in, for example, some diluted milk, it scatters rather brightly. It's not confined to being in a liquid. If you go into the air and have, say, water vapor, shine some bright lights up, you'll get a very beautiful Tyndall effects from all the vapor in the air. So, what is the fundamental origin of light scattering? We've got an electric field going up and down like this. Now, when you impinge upon an atom, you can imagine that you have what's called the positive part and the negative part, and it's going to start oscillating in response to that electric field, which is itself oscillating with the wave's frequency. And as that dipole oscillates in this right-hand panel here, you can see kind of the closed electric and magnetic fields that are produced. Those are kind of pinched off, and then they go and radiate out at the speed of light in the medium scattering is occurring in. So put that together, you have the incoming electromagnetic wave transverse with the electric field vertical in this diagram. You have your molecule here oscillating in response to that wave impinging upon it, and in so doing, it releases radiation. Remember, our take-home lesson in basic electrodynamics is that any accelerated charge will emit radiation. And that incoming wave, by making the dipole oscillate, oscillation is an acceleration, forcibly makes radiation be emitted. Okay, so the type of radiation, we're going to focus on dipole radiation. I mean, there is in metals, you get a very similar effect. It's accelerated charges, but you don't have a dielectric medium that the electrons are tagged to. But most of the materials we're interested in, you have polarizable molecules, whether it's a solvent or a protein molecule or a typical polymer or colloid. And if you look at the pattern that's produced, on the z-axis is the direction of the electric field. What's interesting is there's actually no scattering. If you look at the equation here, this is the scattering intensity. It goes as sine squared phi. Phi 0 is looking straight up. Sine 0 is 0. So there's no scattering in the direction of the electric field itself. Where it's maximum is when phi is 90 degrees. That's in the equatorial plane down here. So that's where you get your highest intensity for regular scattering. And we usually put our detectors in that plane. It's often called the scattering plane. Now, if we go back to this scattering equation again, that's the intensity. There's a few features which are very interesting here. First one is that you can see that the intensity of the scattering goes as 1 over the 4th power of the wavelength of the incident radiation. This means that blue light, which is 400, would scatter 8 times more than, say, 673 nanometers, which is red, and hence you get the blue sky, the blue light coming in. You get white light from the sun coming in, the blue light scattering preferentially, so you see blue on a clear day. Now, this alpha squared here is the polarizability squared. It's a measure of how tightly the electron cloud is bound to its parent nucleus. In a solid particle, it goes as the molar mass squared. And let's consider something that's spheroidal, that it would then go as the diameter to the 6th power. So when you work that out, a single 10 micron dust particle would scatter as much as 10 to the 18th proteins of a diameter 10 nanometers. We're ignoring angular dependence. But that shows you a very important lesson in light scattering practice, is that it doesn't take much contamination by large particles to completely distort the light scattering data that you're getting. So we'll see that several times during this presentation. So it's a reality. You can't really escape it, but you can deal with it in different ways. The 1 over r squared is a manifestation of conservation of energy. It's always good to have a conservation principle involved. The 4th is sine squared phi, which we already talked about, meaning that for regular polarized scattering, when you vertically polarize with your incident beam, you get 0 in the z direction, and you get a maximum in the xy plane, which is where we normally put our detectors. Okay, so just to kind of see it in action, we mentioned the sky is blue. A beautiful day like this, you can see the sky from the Rayleigh scattering. The white clouds is a different matter. We won't go into that right now. But that's also based in scattering from much larger particles than the little molecules of nitrogen and oxygen in the atmosphere. We see when you look towards the sun's vicinity at dawn and dusk, it gets very reddish. That's because the blue light has been scattered away as you look toward the sun's vicinity, leaving the red light. And this is not merely a terrestrial phenomenon. When you go into outer space, you can see here's an example of interstellar dust, the Witch Head Nebula. And if you look closer, you'll see all those fine details, the long pointy nose, the mouth, the chin. If you know about witches, and you can confirm this. I'm from Massachusetts. We have lots of them there. Okay. Now, visible light, where we live and where we perceive with our eyes, is just, as we said before, one part of the very wide spectrum of electromagnetic radiation. So the theories we develop are scalable in terms of the object length divided by the wavelength of the incident light. So if you look at X-rays in the angstrom region, they're about like the spacing in crystals, and so crystallography is typically carried out with X-rays. Whereas when you get to visible light, the particles which are more on its scale, let's say polymers, nanoparticles, viruses, things like that, as you go up to longer wavelengths like microwave and millimeter, you're talking about snowflakes, raindrops, applications in meteorology. If you go up to something as big as airplanes, and radio waves or radar would be used there. But there's a unity in how these are treated. Okay, so let's look at the we're going to just deal with visible light now. So typically between blue 400 nanometers and red maybe late 600 nanometers. And the simplest type of scattering is the so-called Rayleigh scattering. We just gave that formula and analyzed some of its features. Typically, let's say we use a 660 nanometer laser. A native protein in this globular form is typically about 10 nanometers, so it's much less than the wavelength of light, and so it's a good example of a Rayleigh scatterer. The Rayleigh scatterer scatters light equally in all directions in the scattering plane. So this slide here is the plane. It is the scattering plane. It means the electric field is perpendicular to the plane of your screen, and the scattering in the screen, in the scattering plane, is uniform at all angles. Now, as we bring the size of the particle up, for example, protein aggregates, as they get larger, can start to approach the wavelength of light. And then you get preferential scattering in the forward directions. The off-angle pattern here shows many different peaks and valleys of scattering as a function of angle. So that's sometimes called Mie scattering. It involves exact solutions to Maxwell's equations. And normally you need a large number of angles to get meaningful data out of that. So the type of instrumentation will vary as we go through these different types of scattering, but the mechanism is the same. So what do we use light scattering for practically? We can measure equilibrium properties of polymers and colloids in solutions, characteristics such as weight average molecular weight, Z average radius of gyration, the virial coefficients, the second B22 and third B33, also called A2 and A3, the Z average diffusion coefficient, shape parameters, and such. But beyond that, because a lot of solutions are not in equilibrium, for example, an aggregating protein solution, we can actually monitor the time-dependent changes in properties as they evolve, such as, for example, protein aggregation or a polymerization reaction, a degradation of a molecule being broken up, dissolution or phase separations. So you all have probably heard a lot of different light scattering terms bandied about: static light scattering, moles, Rayleigh-Debye, dynamic light scattering. So just a very quick simplified lexicon here. Really, we're breaking this into two types of light scattering. Static light scattering, sometimes called total intensity light scattering, which is just, it means just that. You measure the total intensity of light scattered, normally as a function of angle, and then it's termed moles, multi-angle light scattering. And as mentioned, you can get a weight average molecular weight, virial coefficients, radius of gyration. And then as you go up in size, we already saw you start to get angular dependencies. And so we're still doing static light scattering, but oftentimes we'll be calling it Rayleigh-Debye or ZIM or Mie scattering, but they're all measuring total intensity. Then we go into dynamic light scattering, which is quite different. Again, the mechanism producing the actual scattering is the same, but what we're looking at here is quite different. It's the intensity fluctuations and autocorrelating those, and we'll come back to that. Then there's also a subfield of dynamic light scattering, electrophoretic light scattering, where you can put a charged molecule in an electric field and measure the Doppler shifts or phase shifts using laser scattering. We're not going to go into that today, but that would give you terminal velocity and hence electrophoretic mobility and zeta potentials for charged particles in electric fields. Okay, now the basic setup of the experiment is very simple, and it's in its net form the same for both static light scattering and dynamic light scattering. The details are different on detection and so on, but basically what we have is a laser source nowadays that's almost exclusively used, and then we have the scattering volume. Now let's distinguish that. Usually you'll have a cell, whether it's a flow cell or a batch cell, and the volume of that could be anywhere from 6 microliters on up to milliliters. But the laser going through illuminates only a certain portion, and the detector itself only detects a small portion of the total illuminated portion. That illuminated portion that's detected is called the scattering volume. And it's typically like nanoliters, say 10 nanoliters versus, even if you have a small sample of 10 microliters, which is very small for scattering, this is only 1,000th of that. So it's a very small part of the entire sample you're looking at. Then theta is the scattering angle. Now the direction of the incident beam, its forward direction is designated 0, theta 0. And as we come out from 0, we measure higher angles from 0 to right angle scattering at 90 and then back scattering at 180 degrees. The so-called scattering vector amplitude, or Q, which comes up all the time, is this combination of parameters. N is the index refraction of the medium the scattering is occurring in. Lambda is the vacuum wavelength of the source. And here you have the sign of the half angle. Now the detectors, again, normally is placed in the scattering plane. That's 90 degrees to the electric field vector. Again, here, the electric field vector will be coming out of this slide. And so we have the detector in the plane of the slide. And a difference now, not only do we want a very small area for sampling, so to keep the coherence good for dynamic light scattering. So we need a good coherence, but we also need to sample quickly. The sampling, that's a mistake. That should be 1 microsecond. It's typically 1 microsecond or even faster, not a millisecond. It's microsecond or faster, and that can be supplied by a photomultiplier or an avalanche photodiode. Whereas static light scattering, it's static, kind of says it. It's independent of time, stationary in that sense. You can usually use slow sampling, 1 second, maybe a few hundred hertz if you want to resolve like little scattering spikes, and even longer if you're looking at the long-term phenomena. So for those, you can use photomultipliers, APDs, but you can also get away with very simple photodiodes or CCDs, charge coupled devices. So now let's look at the intensity. If you put your detector here at an angle and just measure the intensity being scattered from any old sample, there's 2 things we're looking at. This is a 0 down here, and this line going through horizontally is an average value of the intensity that's scattered. That's what we're measuring in static light scattering, is that average value. Whereas in dynamic light scattering, you see what looks like fluctuations that could be noise. Well, they're not noise. They're actually rooted in molecular diffusion, which we'll come back to. You're measuring the autocorrelation function of those fluctuations in dynamic light scattering. So we're really looking at different features of the scattering. In static light scattering, we just want that average total intensity versus dynamic, where we're going to do a dynamic autocorrelation of fluctuations. Okay, so let's look at, concentrate on static light scattering, where we're measuring the total intensity. What we have up here is the very famous Zim equation. There's many others out there, but this is a real workhorse because it's proven so useful and practical. What we have in here is a few parameters. So we have our solution with concentration C. Now that concentration, normally measured in grams per centimeter cubed, you either know it because you weighed it out or you measured it with some concentration sensitive detector. Now this K parameter here depends on the index of the medium in which the scattering is occurring, the wavelength of the incident light, that's Avogadro's number there, and this dN by dC is very important. That's the optical contrast between the scatter and the medium it is in. I'll come back to that in a second. But what we want to focus on now is this R here. This is termed the Rayleigh ratio. You can see these units are inverse centimeters. And to interpret it in words, it's the fractional intensity of scattered light per centimeter of, okay, let's say it this way. It's the fraction of incident beam scattered per centimeter of incident path. And then we'll say per steradian of solid angle. You have to integrate overall solid angle to get the total fraction that's been scattered away. But it's independent of your detector's distance from the sample, which is really helpful. And it's also independent of the incident intensity. And so once you have that R, that's what we're going to measure. And we can measure it usually by a calibration to a known substance, whether it's something like a pure substance like toluene at a known temperature, pressure, and wavelength, or even a molecular weight standard. We get this R. So we know K, because it's an auxiliary parameter. We either determine C by measurement or know it from weighing it out. And then we can get from this equation the weight average molecular weight, the Z average mean square radius of gyration, and the second variable coefficient, and maybe the third. And you'll notice there's a restriction, which is that Q vector squared times the Z average mean square radius of gyration, that product should be a lot less than 1. Okay, now we mentioned the optical contrast is a very important feature because you'll remember this experiment. You take a piece of glass and you can see it in the air. When you dunk it in a beaker of water, you can still see it, but it's a lot less visible than it was in air. And then if you dunk it into toluene, it pretty much disappears. The reason being the indices of refraction of glass, typical glass and toluene, are almost the same. There's no contrast, so it becomes invisible. So it's the same thing when we put scatters in a solvent. For example, here's some carbon disulfide. We put in polybutadiene and polystyrene. And what's very interesting is the polystyrene scatters nothing. It has the same index of refraction as the medium, whereas the polybutadiene scatters significantly. It has a reasonably different index of refraction. So its dN by dC is non-zero, whereas for the polystyrene, it's virtually 0 here. Now, if we go to a different solvent, in this case, go to orthoxylene, you see now the polybutadiene has become virtually invisible, and the polystyrene stands out. So that's a technique for playing with copolymers and terpolymers and such, you can isolate and analyze the different components using different solvents. Now, when you're an aqueous solution, like most protein work, a good rule of thumb is that almost anything that will truly dissolve in water has a DN by C pretty much in the range of 0.1 to 0.2 centimeter cubed per gram, with some exception, but you're generally in there. Whereas when you're dealing with organic solvents, it can be all over the map. You see two cases here where it's 0, and it can be negative, and it can be positive, so it's quite different in organic solvents. Okay, now we mentioned the Zim equation. Let's look a little more closely at that. The old traditional way of doing these was to make up fixed concentrations. Here we have 1, 2, 3, 4, 5 concentrations over multi-angles. In this case, there's 7 angles, and then you measure each of those, and then you extrapolate here to 0 angle, and then you can see 0 angle means Q goes to 0, and so what you have left is a line whose intercept is 1 over the weight average molecular weight, and whose slope is twice the virial coefficient. Then you can take and extrapolate to 0 concentration here, and then this term goes away, and what you then have left is, once again, a line whose intercept is the same 1 over mw. They both give the same intercept, but its slope now is related to the z average mean square radius of generation. Okay, well, we talked about a z average, talked about a weight average. Let's look a little bit into what we mean by those averages. So, unless you're dealing with something like a monodispersed protein, for which there's only a single molecular weight, most species have some spread in their sizes, a distribution of sizes. Almost all our synthetic polymers have a distribution of sizes. Even natural products like polysaccharides will have distributions of sizes. So you have some curve here, that's the size distribution curve, and we define different averages. See, the weight, the number average, MN, is what we're all most used to. It'd be like sum up all the grades in the class and then divide by the number of students in the class, and that gives us the number average grade in the class. Now, the weight, if you did that, the weight average, it would be pretty funny. You'd take each student's grade and multiply it by their weight and add that all up and then divide by the total weight of students in the class, and that would give you the weight average. Now, it's, virtually farcical to do that in a classroom, but with polymers, it's very important, because if you look at this distribution, it's, hate to be a pun, but it's a weightier average than M sub n. M sub n is looking at the low mass portion of your distribution here, whereas MW comes close to more representing where most of the mass of your polymer or your other sample is located. So it's a very good average, and if you're on a desert island and had to pick one average to know, it would be the weight average. Whereas the Z average, you can see it involves the mass squared. So this, going back to the classroom analogy, you would multiply each student's test score times their mass, their weight squared, and add that up. And you see, it would really, really emphasize the heavier people in the classroom. You wouldn't normally do that. Don't normally do that in polymer analysis either, but it sometimes comes out as the average is measured. In fact, we've defined these for mass, the N average, the weight average, the Z average, but they exist for other quantities. For example, we already mentioned the Z average mean square radius of gyration and the Z average diffusion coefficient. We'll come back to some of the practical consequences of that shortly. So for example, Z average diffusion coefficient. Now let's see how those different averages react to a distribution, and let's, for argument's sake, we have 50 small particles, just for example, proteins that are intact, and then we have here 2 big particles, or 10 times the mass of the proteins. They might be aggregates, they might be dust particles. And what you see is that if you look over here, when you're summing up the moments, one involves concentration, the other is mass times concentration. Remember, the Z average is going to be mass squared times concentration. You can see how these build up very quickly. We're on a log scale here, so you get really big numbers as you go from number to weight to Z average. And when we actually look at those averages, we see the number average between 1 and 10 is 1.35. So it really is more toward where most of your particles are. 1.35 is closer to 1 than 10. Now the weight average is in between. It's 3.57. So now it's further up from 1, but it's giving more proportion to those large particles. Whereas when you go to MZ, you're almost pegged up at 10. You're at 8.2. So it's very strongly emphasizing those two big particles at the expense of the very small ones. Okay, so we mentioned the second virial coefficient, B22, also termed A2. What does this mean? It's basically related to the volume excluded between two particles. And one way to think of this is, when you talk about an ideal gas, for example, those are point particles. That's what you learned, the ideal gas equation. Those point particles don't interact with each other at all. They go right through each other. Then you had van der Waals that came along and came up with that equation, which took account of the fact that the molecules actually occupy space and hence can repel each other by steric effects, and they can also attract each other by usually dipolar type forces or van der Waals forces. And the B22 then is related to that volume that's excluded, so it has to do with the size of the particles with respect to each other, and that size can also include a so-called electrostatic or soft size, which we won't go into. But the relationship is really the excluded volume divided by twice the mass squared, so it's excluded volume per mass squared. An example would be, let's say you had two proteins that were spherical and they can't interpenetrate each other. The closest they can get is for them to touch. And then the excluded volume is this dashed line sphere, which you can see has a radius of twice r. And so the excluded volume is 4 pi over 3 times 2r cubed. So you get 32 pi r cubed is this excluded volume. And then you multiply Na over 2m squared, you got your B22 for hard spheres. Now the B22, this is a really simple case where you just have a sphere that's uniform all the way around, spherical symmetry. A lot of times you don't have that. For example, proteins can have very complex surfaces with nooks and crannies and different charge densities and hydrophobic patches and so on. So this B22 is actually, it integrates it all up into a single number, all the repulsions, all the attractions in these complex systems. So it's kind of like a nice handle on net interactions. It's attractive, it's repulsive how much. In fact, so broadly, if B22 is greater than 0, if it's positive, it means you have net repulsion. If it's 0, there's no interaction. It's just like an ideal gas between the particles. If it's less than 0, there's net attraction. Now, how this shows up when you do your light scattering experiments, here's the Zim equation in the limit of 0 angle. So that could either be really small particles like native proteins, or it could actually be multi-angle data extrapolated to 0. And what you see is you're going to get an intercept that we saw before, 1 over the molecular weight, and then it's going to go up linearly at low concentration. So here's 3 different proteins, are actually monoclonal antibodies, 2 different types in their own buffers, and you can see they go up linearly, and that slope then gives us the virial coefficient, second virial coefficient. Now, a lot of times people will do experiments at a fixed concentration and don't have the luxury of extrapolating to 0. So the question is, how big of an error would you get if you did experiment at fixed concentration and didn't extrapolate to 0? Well, you can estimate that the fractional error in the molecular weight is twice the virial coefficient times the concentration you're at times the weight average molecular weight. So to put some numbers on that, let's say we're talking about a monoclonal antibody of 150 kilodaltons, or 150,000 grams per mole, and a second virial coefficient 5 times 10 to the minus fifth, and check out the units, centimeter cubed mole per gram squared. But if you put that into our fractional error equation, it all depends on the concentration. So if we're at 10 to the minus fourth gram per centimeter cubed, that is 0.1 mg per mil, you have less than 1% error. 0.15% error. If you go up to a mg per mil, you're at 1.5% error, not too bad. At 10 mgs per mil, now you got a 15% error, and it's up to you whether you consider that too much or not. By 50 mgs per mil, you have a 60% error. That just gives you an idea of what happens if you don't extrapolate, the kind of errors you can engender. Now, as we saw, we'll go back to here for a second. You can see there's that was a linear term at low concentrations. You go to higher concentrations, you're going to get quadratic and cubic terms due to the third and fourth virial coefficients. And the way they'll show up, now notice here I'm plotting the intensity directly. rather than the reciprocal, which is what we did previously. I'll come back to that. But the reason I'm showing it this way is that in an ideal situation, that is like an ideal gas where there's no virial coefficient at all, the light scattering would just go up linearly with concentration like you see for this one here. But for these other ones, you can see it start to curve over, negative second derivative. That's the effect of the second virial coefficient. The fact that it reaches a peak and then comes down is due to the higher virial coefficients. For example, if you have a third virial coefficient, that will cause it to come down as you increase your concentration, and the fourth can push it along its way to come down as well. Now, if we go back to the previous representation, reciprocal, Kc over R, the product versus concentration. Remember, it was linear at low concentration, but as you ratchet up the concentration, you get to develop that quadratic shape, which is due to the third virial coefficient. So a number of people use the virial coefficient to try to make predictions about protein stability. The general rule of thumb is that the higher the value of the second virial coefficient, the more liable the protein is to stable it is, more liable it is to be stable, although not always. And another one is if you could measure B3, a third virial coefficient, that usually gives even greater stability. Again, not always. So kind of suggests that you do this dynamically, watch it in real time for aggregation, but we're not going to talk about that much today. Now, the question frequently arises, what's the lowest molar mass that we can measure with static light scattering? And the answer is, well, it doesn't really depend on the lowest molar mass. It depends on this product of factors. So the Rayleigh ratio, remember that's what we're measuring with our static light scattering total intensity measurements, is the product of that optical constant, which involves the contrast, dN/dC squared, the concentration you're at, and the weighted average molecular weight. So it involves all three of those. Now, for a given material, for example, given water-soluble polymer or protein, K will be fixed. So it's really C times MW, which is going to determine everything. And really, this is just a function of the quality of your light scattering instrument. You know, how low can you reliably measure R? That's all it is. So here's just a typical example of, say, measuring toluene over time, and you can see it has a certain noise level in that baseline, mostly thermal, and a little bit of short-term drift. So you basically get a signal-noise ratio or noise-to-signal ratio, which will determine how low you can go for. So remember, it's that product minimum that counts. So the minimum of Kc times MW will be your noise-to-signal ratio times R of a standard that's used. In this case, we're using toluene. And then N is the number of standard deviations you're willing to accept as proof that you've made a valid measurement. I think in particle physics, it's usually 5 sigma. Let's say we take 6 sigma. Okay, so we're comfortably out of the noise baseline and we have a certain measurement of R. And so if we take 6 sigma, let's take an example then of a fixed K. So this will be water with a dN/dC of 0.18, typical for a protein. We're using toluene. We had a noise of signal 0.05. We're taking 6 sigma. And then what you can see is that in order to measure with reasonable accuracy molecular weight of 1,000 daltons, 1,000 grams per mole, it would take 3 mg per mil. 10,000 would be 0.3 mg per mil. 100,000 molecular weight would be 0.03, and so on. So it really is a function of concentration for a fixed material and a fixed solvent. That's how good your system is. Okay, let's move over to dynamic light scattering. And remember, we showed this slide earlier where what we've been talking about till now, the static light scattering is a straight line going through the average value. Now let's look at those fluctuations. And first of all, what do they do to? You shine this light on this solution containing particles. If you think about it, each particle is scattering off light and it's going off to a detector. And each one does that. Now, they're at different distances away from the detector, which means each scattered ray or scattered wave travels a different path length. That means it has a different phase with respect to all its neighboring phase shifts from all the other particles. So what you see, whether it's your eye or a detector, is a complex interference pattern that involves summing up all the phases of these particles wherever they stand at that instant. It's that interference pattern. But these particles are not sitting still. They're diffusing about, which means the phase of each one of those is changing in time, meaning the pattern intensity is changing in time. So you can see that this is an example. The intensity is going up and down. This is not noise. This is due to the fact that the particles are diffusing and changing the interference pattern at the detector. And what we see here is what you'd expect. Smaller particles diffuse more quickly, and so you get a more quickly varying set of fluctuations out of the small particles. Okay, that's a misnomer. That should be as a function of tau. Anyway, here is correctly represented as C at Q tau. It comes down and goes down essentially to, if you subtract off the baseline, it'll go down to 0. And the ones for the large particles decay more slowly than the small particles. You have a faster decay. So what you do with that is, now, as we all know, when you get a dynamic light scattering instrument, everyone says, well, what was the hydrodynamic diameter or the hydrodynamic radius? I'll talk about radius. We use R sub h instead of D sub h, because D we're reserving for the diffusion coefficient, which is what you actually measure in a Brownian motion system. So the autocorrelation function that we just discussed is actually not directly related to the diameter that we think we're quoting. It's actually related to the Z average mutual diffusion coefficient of the particles, D sub Z. So we already know about Z averages. They emphasize very large particles at the expense of the smaller ones. In the limit of 0 concentration, this mutual diffusion coefficient becomes the self-diffusion coefficient, how the particle diffuses in the absence of effects from any other particles. So what we would measure at a finite concentration is the 0 diffusion coefficient, Z average, times 1 plus C in a proportionality factor, which is K sub D. So it's kind of like a hydrodynamic variable coefficient. And it's very popular to use these days for various purposes. But to actually get a diameter out of this, we have to extrapolate to concentration 0. And then once we have we can only talk about monodispersed particles. So it's really nice if you have, say, some latex particles, which are nice and monodispersed, or some intact proteins, which are fully monodispersed. Then we can go ahead, and they're spherical, use the so-called Stokes-Einstein equation, which is specific for spherical particles and spherical particles only, which then relates the diffusion coefficient, the self-diffusion coefficient, that is at 0 concentration, to a hydrodynamic radius or a hydrodynamic diameter. And you have Boltzmann's constant T. This is viscosity of your liquid here. So that you can unambiguously measure for monodispersed spheres. Now, when you get polydispersed spheres, what we actually measure is a Z average diffusion coefficient when you do a cumulant expansion, and then what we're calling the Z average hydrodynamic radius is actually a very peculiar quantity. It's the reciprocal of the Z average of the reciprocal hydrodynamic radius. Okay, I'm not going to go into that anymore right now, but it does show it's a fairly complex average. Now, what's the measurable size range for spherical scatters using DLS? Typically a nanometer to 2 microns. And it's not just spherical scatters. You can measure polymers and little rods and other shapes as well. But that's pretty much your range where this technique is robust. Now, it's also one of the most perilous techniques out there, just because it's been made very simple in its operation. You can put in a sample, hit a button, and get an answer. What we've started off here with was the fact that even small amounts of large particles can drastically affect your scattering, and when you do dynamic light scattering, the effects come in as a Z average. So you really, if you want to be doing dynamic light scattering and getting meaningful answers, you really have to scrutinize the autocorrelation functions you're getting. This green one here is a good one, like we showed previously. It's smooth, comes down to 0 at the baseline. Bad correlation functions look like, say, this orange one, which kind of meanders around and bumps, and only way out does it go down to 0, or one that comes down with bumps in it, and then takes a long time to get down to zero. Those are bad autocorrelation functions. Notice here, if you do have these large particles in there, like dust, we already said that one 10 micron dust particle can scatter as much as 10 to the 18th, 10 nanometer proteins. They're big enough that when they go through the scattering volume, they can produce their own spikes. It's kind of like when you look at a sunbeam coming through a window and see dust particles dancing and sparkling in the sunlight. You can actually see that with your detectors when dust comes through, but it has a horrible effect on the autocorrelation function. There are some softwares which attempt to suppress the dust thresholds and so on. And the other way around it is to try to come up with actual distributions from the autocorrelation function instead of just a Z-average diffusion coefficient. That's something which has involved many, many years of development. It's something that some people will take unequivocally as like, here's my distribution. Other people are more cautious, as they should be, knowing that these distributions have to be taken with a grain of salt. There are many approaches to that. I won't go into that now, but it is cautionary to believe these distributions literally. Usually we take the Z-average from the cumulant, and if it's not too polydispersed or contaminated with dust or other particles, it can be a very good value. Okay, well, I'm getting toward the end now. And we've been talking about equilibrium systems up to now, and I mentioned at the beginning that we can also use light scattering to monitor non-equilibrium systems. And when you get into living systems, we are not in equilibrium. We're far from equilibrium. We have a flow of energy coming through, producing the energy of life, and then producing entropy as waste. And when you reach equilibrium, you're dead. So some of the time-dependent processes we could look at in macromolecular solutions or colloid solutions include aggregation, degradation, phase separation, dissolution, supramolecular assembly, polymerization process itself, crystallization. And in all of these, a key notion is that the molecular weight of the scatterers is changing, whether they're getting smaller because it's a polymer being chopped up, or bigger because you're forming a polymer or you're aggregating a protein. The molecular weight is changing. And the total intensity light scattering, that intensity is exquisitely sensitive to the mass. It's directly sensitive to the mass. So the other feature of the static light scattering is you can measure it instantaneously, so you can follow continuously a process. So examples would include, here's a polymerization reaction. It's actually some acrylamide being polymerized, and you can see generally the light scattering going up in time. Those signatures can be related back to the kinetics and molecular weight of the reactions. Another example is where we have hyaluronic acid, and it's being endocytically chopped up by hyaluronidase. The light scattering as the function of time is coming down as you make smaller and smaller fragments. That type of data can be analyzed to give you Michaelis-Menten parameters of efficiency and max turnover of an enzyme, for example. And another example is protein aggregation here. What we're plotting in this diagram is the weight average molecular weight of all scatters, and everyone knows what that is. But it's all scatters. It's the intact protein plus aggregates, and we're dividing out by the native intact protein molecular weight. So MW over M0 means you have no aggregates at all. So we started with a nice clean solution here. Here it was a monoclonal antibody. We applied a stress, and you can see at 30 degrees going out to 6 days, but the logarithmic scale. It was stable. When we went to 45, you can see it was starting to go unstable after several days. 50 degrees even more quickly, and by the time you're at 83, the instability is a matter of tens of seconds. So extreme sensitivity to temperature for this aggregation process. Point here is that we're measuring it in real time. And there's analyses that go along with that that we're not going to go into. I think I'm at my time's limit. So to summarize, static light scattering is applicable over a wide range of sizes from less than a nanometer up to hundreds of microns. Now, the way that static light scattering is measured, there's many different types of instruments, and then the theories that are used to reduce the data and interpret the data they change markedly over this regime, so you don't have a single instrument that does it all, but they're all based on the total intensity scattering principle. Another good thing as mentioned is you can measure it instantaneously, the intensity, so it lends itself well to continuously following dynamic processes. Also, when you do have things like dust spikes or particle spikes, you can eliminate those and get back to your baseline. And you can usefully count those spikes if you want to do particle characterization, like the number of large particles per centimeter cubed. We already mentioned that SLS is typically used for these parameters here. Won't repeat that. For 100 nanometers to 100 seconds, hundreds of microns, the Me scattering normally measures particle size as opposed to weight average molecular weights and virial coefficients. Dynamic light scattering, about a nanometer up to a couple of microns. That's measuring a Z-average diffusion coefficient, which is related at zero concentration to an equivalent sphere, diameter or radius, and in a highly polydispersed system, the relationship is more complex. DS also requires an integration period. Quality of systems now is such that you can typically get away with 5-10 second integration and get reasonable data, but it is not continuous and it's harder to eliminate points, but it's still a very widely used and valuable, robust technique. And as we've seen, SLS and DLS are, by the nature of light scattering, are inherently biased toward small amounts of large particles. Static light scattering by a weight average mass, and then DLS even more by a Z-average diffusion coefficient. And with that, I think we're at the end. Thank you.
Thanks, Professor Reed. At this time, if you have any questions, you can post them in the chat feature or using the Q&A feature.
Okay, so I'll ask a question just to get this started. Wayne, on the DLS autocorrelation, you showed a couple examples, the orange line that was not a very good correlation and the line underneath that. What's the final consequence of assuming that that autocorrelation is a true representation? What's the consequence of making that assumption?
Well, usually in those cases, the function has either been distorted because of a transient presence of, say, large particles going by, in which case you'll get a false reading, or the system is inherently so polydispersed that it's really not meaningful to analyze this way.
Right, okay.
All right. It appears that we don't have any more questions, so we'll go ahead and wrap up the webinar at this time. I want to thank Professor Reed again for conducting the webinar, and I want to let all of you know that in the next couple of days, I'll send out the recording of the webinar presentation as well as a PDF of the PowerPoint deck. And we'll take questions at that point. If you have any questions that you forgot to ask, you can share them at that time. So thanks again for joining us, and hope to speak with some of you very soon.